Preparing for a Databricks ML Engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design an end-to-end machine learning pipeline in Databricks? I would design the pipeline as reproducible stages. Ingest raw data into Delta tables, validate quality, transform features, train models, evaluate them against business and technical thresholds, and register the approved version in MLflow. Databricks workflows would orchestrate dependencies, with separate development, staging, and production environments. I would add data drift, performance, latency, and cost monitoring, plus rollback procedures. The key principle is that training and serving use consistent transformations and versioned inputs. While answering, focus on data ingestion, feature preparation, experimentation, training, validation, registry, deployment, monitoring, and orchestration. Explain how Delta Lake, notebooks, jobs, MLflow, and production ownership fit together. Question 2. What is the difference between Delta Lake and a traditional data lake? A traditional data lake usually stores files cheaply but leaves consistency and governance to surrounding systems. Delta Lake adds a transaction log, enabling ACID writes, schema enforcement, schema evolution, time travel, and reliable concurrent reads and updates. For machine learning, that means I can reproduce the exact training dataset, inspect historical versions, and prevent malformed data from silently entering a pipeline. It also supports efficient upserts, which are valuable for incremental ingestion and feature maintenance. Make sure to cover ACID transactions, schema enforcement, time travel, reliable concurrent writes, data versioning, and operational recovery. Relate these capabilities to reproducible machine learning datasets and trustworthy production pipelines. Question 3. How would you prevent training serving skew? Training serving skew occurs when features are computed differently offline and online. I would minimize it by defining transformations once, versioning feature logic, and reusing governed feature definitions for both training and inference. I would enforce point-in-time joins during training so future information cannot leak backward. Before release, I would compare offline and online feature distributions, run shadow predictions, and monitor discrepancies. If skew appears, I would stop promotion rather than accept degraded model quality. In your answer, discuss shared transformation logic, feature versioning, point-in-time correctness, online and offline consistency, validation tests, and monitoring. Mention how Databricks tools can centralize governed feature definitions. Question 4. Explain how you would use MLflow in a Databricks project. I use MLflow to make experimentation and promotion auditable. During training, I log parameters, metrics, datasets, code references, artifacts, and the model itself. I then compare runs using consistent evaluation data, register the selected model, and promote it through controlled environments with approval checks. In production, I track the deployed version and associate predictions with model metadata. This creates a clear path from experiment to deployment and makes rollback straightforward. Be sure to mention experiment tracking, parameters, metrics, artifacts, model packaging, registry workflows, aliases or stages, deployment, and lineage. Connect MLflow usage to reproducibility, collaboration, and controlled promotion. Question 5. How would you optimize a slow Spark-based feature engineering job? I would begin with Spark UI and the physical execution plan to identify whether the issue is skew, excessive shuffling, small files, or inefficient transformations. Then I would filter and select columns early, use appropriate partitioning, broadcast genuinely small lookup tables, and avoid unnecessary Python UDFs. I would compact files and enable relevant delta optimizations where appropriate. Finally, I would benchmark each change, because a faster stage can still increase total cost or create downstream imbalance. Focus on identifying the bottleneck first, then discuss query plans, partitioning, file sizes, joins, shuffles, caching, predicate pushdown, and cluster configuration. Include measurement rather than assuming optimization works. Question 6. What causes data leakage, and how would you detect it? Data leakage happens when training uses information unavailable at prediction time. Examples include a post-outcome status field, a randomly split time series, or normalization fitted on the full dataset. I would inspect feature timestamps and business definitions, use time-based splits when appropriate, fit preprocessing only on training data, and challenge unusually strong validation results. I would also build feature availability tests. A model that performs slightly worse but reflects real deployment conditions is more valuable. In your answer, distinguish target leakage, temporal leakage, and preprocessing leakage. Explain temporal splits, feature availability checks, pipeline isolation, suspicious validation performance, and review of data generation timestamps. Question 7. How would you choose an evaluation metric for an imbalanced classification problem? I would start with the cost of false positives versus false negatives and the action taken after a prediction. For rare events, accuracy is usually misleading, so I would examine precision, recall, PRAUC, and a confusion matrix at the operating threshold. If predicted probabilities drive decisions, I would also assess calibration. I would select the threshold using validation data and confirm performance across important segments. The final metric should reflect business value, not simply maximize a convenient score. Make sure to connect the metric to business costs, prevalence, ranking versus probability quality, and operating thresholds. Discuss precision, recall, PRAUC, calibration, confusion matrices, and segment-level evaluation. Question 8. Describe how you would deploy a machine learning model for real-time inference. I would first define latency, throughput, availability, and accuracy requirements. The model would be packaged with its exact preprocessing dependencies, exposed through a versioned endpoint, and supplied by reliable low-latency features. I would load test expected and peak traffic, configure autoscaling, and monitor latency, errors, resource use, feature drift, and prediction quality. I would deploy using canary or shadow traffic, retain a previous version for rollback, and design a safe fallback when features or the endpoint are unavailable. Cover latency and throughput requirements, feature availability, model packaging, serving infrastructure, autoscaling, validation, observability, fallbacks, and rollback. Explain how you would balance responsiveness, reliability, and operating cost. Question 9. How do you handle concept drift after a model is deployed? Data drift means inputs change, while concept drift means the relationship between inputs and outcomes changes. I would monitor feature distributions continuously, but evaluate true model performance once delayed labels arrive. Retraining should be triggered by sustained performance degradation, meaningful distribution shifts, or business changes rather than one noisy period. I would compare a challenger model against the champion, validate it on recent and historical slices, then promote it gradually with rollback protection. Discuss the difference between data drift and concept drift, monitoring signals, labels arriving later, retraining triggers, champion-challenger testing, and safeguards against reacting to temporary noise. Question 10. What is a feature store, and when would you use one? A feature store manages the lifecycle of reusable machine learning features. It typically provides an offline store for historical training data and an online store for low-latency serving. I would use one when multiple models share features, when consistency and lineage matter, or when online inference needs reliable feature retrieval. Important capabilities include point-in-time correct training sets, access control, freshness monitoring, and ownership. I would not introduce it solely for a small, isolated batch model. In your answer, explain reusable feature definitions, offline and online stores, discovery, governance, point-in-time joins, serving latency, and why a feature store is valuable for multiple teams or models. Question 11. How would you build a reliable batch inference pipeline? I would make the job idempotent by assigning each input record a stable key and writing predictions with a model version and processing timestamp. The pipeline would validate schemas, handle incremental data through a reliable watermark, and write results transactionally to Delta. I would configure retries for transient failures, alert on missing partitions or abnormal volumes, and preserve checkpoints. Rerunning a failed interval should replace or safely merge outputs rather than create duplicate predictions. Focus on idempotency, incremental processing, input validation, model versioning, output checkpoints, retries, observability, late data, and downstream handoffs. Mention how reruns should avoid duplicate or inconsistent predictions. Question 12. How would you improve model reproducibility across experiments and environments? I would version the code, training data reference, feature definitions, configuration, dependencies, and model artifact for every run. MLflow would record parameters, metrics, and lineage, while a reproducible environment would pin library versions. I would control random seeds where possible and use deterministic evaluation datasets. I would separate environment-specific settings from code and automate training through a job rather than relying on notebook state. That allows another engineer to recreate, audit, or challenge the result. Be sure to mention versioned data, code, dependencies, random seeds, environment specifications, model artifacts, configuration management, and deterministic evaluation. Explain why reproducibility supports debugging and governance. Question 13. What is your approach to model explainability and responsible AI? I treat explainability as a decision support requirement, not merely a visualization. I would provide global behavior summaries and local explanations appropriate to the model and audience, while clearly stating that feature attribution is not causal proof. I would test performance and error rates across relevant groups, protect sensitive data, document intended use and limitations, and retain human review for high-impact decisions. After deployment, I would monitor fairness and explanation stability because model behavior can change. Discuss audience-specific explanations, global and local methods, feature importance limitations, fairness testing, privacy, documentation, human review, and monitoring. Emphasize that interpretability does not automatically prove causality. Question 14. How would you diagnose a model whose production accuracy suddenly falls? I would first confirm that the metric drop is real and that labels are complete and correctly joined. Then I would compare production inputs with training distributions, inspect schema and pipeline changes, verify preprocessing parity, and segment errors by geography, product, or customer type. I would check serving logs, latency, missing features, and model version changes. If impact is material, I would roll back or activate a fallback while investigating, then add a regression test for the root cause. In your answer, establish a structured diagnosis, label timing, data quality, schema changes, drift, serving differences, infrastructure failures, segment performance, and recent releases. Include containment before root cause analysis. Question 15. How would you handle class imbalance during model training? I would preserve a realistic validation and test distribution, then address imbalance in training through class weights, targeted sampling, or carefully validated synthetic examples. I would select metrics such as recall, precision, PRAUC, and expected business cost rather than accuracy alone. After training, I would tune the decision threshold and check calibration. I would also inspect performance by segment, because an aggregate improvement can hide unacceptable recall for a smaller but important population. Cover the business objective first, then stratified or temporal sampling, class weights, resampling, threshold tuning, appropriate validation, calibration, and avoiding synthetic data artifacts. Explain why accuracy alone is insufficient. Question 16. When would you use pandas, UDFs, or native Spark functions? I prefer native Spark functions because they are optimized, distributed, and visible to the Catalyst optimizer. I use pandas when the dataset comfortably fits in local memory and the workflow benefits from local analysis. Pandas UDFs are useful for vectorized Python logic that cannot be expressed natively, but they add serialization and memory considerations. I would avoid collecting large data to the driver, test representative workloads, and inspect execution plans before choosing an implementation. Explain the trade-off between simplicity and distributed scale. Cover native Spark functions first, pandas for small local data, pandas UDFs for vectorized distributed logic, serialization overhead, memory limits, and performance testing. Question 17. How would you secure sensitive data in a Databricks machine learning workflow? I would apply least privilege permissions to workspaces, clusters, data, feature tables, and model registries, using group-based access rather than shared credentials. Secrets would be stored in a managed secret system, never notebooks or source control. I would mask or tokenize sensitive fields, restrict columns and rows where necessary, encrypt data in transit and at rest, and audit access. I would also prevent sensitive values from appearing in logs, experiment artifacts, or model explanations. Mention least privilege access, workspace and storage controls, secret management, encryption, row or column restrictions, audit logs, masking, environment separation, and minimizing sensitive data in notebooks and artifacts. Question 18. How would you reduce the cost of a Databricks ML workload? I would begin by separating compute cost from storage and identifying expensive stages or experiments. I would use right-sized job clusters, autoscaling with sensible bounds, automatic termination, and appropriate instance types, rather than leaving interactive resources running. Incremental processing, efficient delta layouts, column pruning, and avoiding repeated feature recomputation can reduce runtime substantially. For experimentation, I would limit broad hyperparameter searches, reuse valid artifacts, and track cost alongside model quality so optimization does not become blind. Focus on workload measurement, right-sized clusters, autoscaling, job clusters, instance selection, caching decisions, incremental processing, file optimization, experiment management, and stopping idle resources. Question 19. How would you productionize a notebook-based prototype? I would first identify the notebook's inputs, outputs, assumptions, and business logic, then move reusable transformations and training code into tested modules. The notebook can remain an exploration interface, but production execution should be parameterized, source-controlled, and run through a scheduled workflow. I would pin dependencies, add data quality and unit tests, capture structured logs, and register artifacts through MLflow. Promotion would require validation checks and review, creating a repeatable release rather than a manual copy. Discuss separating reusable code from exploration, parameterization, testing, packaging, source control, job orchestration, environment management, logging, monitoring, and deployment gates. Explain how you would preserve speed without preserving fragility. Question 20. Tell me about a machine learning project where you made a difficult engineering trade-off. In one project, a complex model improved offline AUC by 3 points but exceeded our latency budget and required fragile real-time features. I compared it with a simpler model, measured business impact at the operating threshold, and chose the simpler option after confirming only a marginal production lift from complexity. We deployed it with better monitoring and faster retraining. The lesson was to optimize for reliable business outcomes, not an isolated leaderboard metric, while preserving a path to revisit the decision. While answering, structure the story around context, alternatives, measurable constraints, decision, implementation, outcome, and lesson learned. Quantify impact and show collaboration, ownership, and awareness of second-order consequences. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.